This PowerPoint is over sound. This is a lab that we do in class. Sound waves. Sound waves are longitudinal that travel through air. The loudness refers to the amplitude of the energy that the sound wave is carrying as measured in decibels. Now this is not a linear system, which means twice the loudness doesn't mean twice the decibels. It's actually a logarithmic scale, which means that if you have twice the decibels, that's actually 10 times louder. Basically, long story short, it's not going to be a linear relationship between the loudness and the decibels. Next is pitch, and that's the perceived frequency by the ear and the brain. That's also not a linear relationship, but it is a relationship that is proportional in that when the pitch increases, the frequency has increased also. But the reason it's not directly proportional is because if I double the frequency, that doesn't sound like I double the pitch of that sound. So they do both increase and decrease with each other, but it's not a linear relationship. Producing sound, in order for an object to produce sound, and this is basically anything that we can think of, there is some sort of vibration back and forth, and that vibration back and forth, basically what it does is it pushes the air one way and then pulls back the other way, so it makes your compression and makes your rarefaction. So you got your higher pressure and your lower pressure, and basically that's what sound is made from. Sound's made from these higher pressures and lower pressure that in a pattern. Then that pattern is basically the frequency at which the compressions and rarefactions are created. So the vibration of this back and forth, the number of vibrations per second, is the frequency that it vibrates back and forth, and it produces a sound with the same frequency as it travels through the air. Now that works for a tuning fork, but what about other things? Let's say a guitar. A guitar has a vibrating string, and that string vibrates back and forth, and how often that string vibrates back and forth depends on a couple things. It depends on the tension in the string. The more tense it is, the more it vibrates back and forth. But also the thickness of the string. The more mass it has, the harder it is to vibrate back and forth. So the more mass it has, it's actually going to vibrate back and forth less. If we think of a trumpet is actually your lips that are vibrating back and forth, that are creating that sound inside of a tube that's in a bent pattern. Let's see, if you think of a flute, then that's also going to be the vibration of your lips, or actually the sound inside the air inside the tube. A trombone is also going to be the vibrations of your lips. A clarinet is going to be the reed that's actually vibrating back and forth. So basically, anything that makes a sound is some sort of vibration back and forth that causes a compression and a rarefaction. So how do we perceive these sounds? Well, basically what happens is as the sound comes in, you got the ear right here that confines that sound down into the ear canal, and basically it amplifies it a little bit by making it go through the ear canal. And when it goes through the ear canal, you got compressions and rarefactions, and the compressions push on the eardrum and the rarefactions pull away from the eardrum, and that compression and rarefaction, the frequency of that, it basically is matched by the frequency of the eardrum being pushed and pulled back. And then that frequency is then goes through these three bones right here, the hammer, the anvil, and the stirrup, and those vibrations go into the cochlea. And the cochlea, basically what it's confined, what's inside the cochlea is you got a liquid that does two things. Number one, it helps you with balance, and number two, it takes those vibrations and sends them to little hairs that are on the outside of the inner lining of the cochlea, and those hairs have different lengths, and those lengths correspond to basically which hairs vibrate with which frequencies. The higher frequencies, the faster it vibrates back and forth, you get the smaller hairs that correspond to those, and when those hairs are interrupted, it sends an electrical signal up the auditory nerve to the brain that lets the brain know that sound is being heard, or that hair is being vibrated. Also, this canal right here, that goes to the nasal cavity, and what that does is that allows air pressure to come in behind, and since this eardrum closes off the ear canal from inside here, that canal allows the pressure, like if you go up in an airplane, you got higher pressure inside the cabin, and that pressure, as it's being pressurized, you get a different pressure on the outside than on the inside. So when you yawn or chew gum or something like that, it allows the pressure to equalize. The range of hearing that we can hear, we go from the lowest end, which is 20 hertz, that's 20 cycles per second, up to the higher end, which is 20,000 cycles per second. And you can see that the range that we have here, music is generally in this area, speech is generally in this area right here, from 100 to about, I guess that's 700 or 7,500 hertz or something in that range. And then this side we have the intensity, and this kind of deals with loudness, but the watts per meter squared. So that's basically power per unit of area. As that increases, you get up to a threshold of pain up here that anything above that is going to cause some damage to your ear. Below this, you're not going to be able to hear. And you can see as you increase the frequency that you can hear things at a lower intensity. But at 20 hertz or 50 hertz, you got to have a pretty high intensity. It's got to be pretty loud in order for you to actually hear those frequencies. These simulations are done in class, and I would suggest, if you haven't gone to these or seen this, you go to this website right here and play around with this yourself. We can measure the speed of sound using two different methods, where we use velocity is going to be distance divided by time, or velocity equals wavelength times frequency. Also, if you have two sources that are interacting, you have two sources of sound, those sources of sound are going to interact with each other, and you're going to have sound that's actually going to have constructive interference and destructive interference. And then varying air pressure. Actually, if you take all the air pressure, all the air out of a room, then the sound will not be able to move forward, because anything that creates sound has to have a medium through which it moves through. So if you remove all that air, then you're not going to have any sound that's going to be created. In talking about sound interference, basically you got your two sources right here. You got the light blue represents a compression, and then the white part in between the light blue, that's going to be a rarefaction. So compression, rarefaction, and so on and so on. And then source B has the dark blue, and it has its compressions and rarefactions also. Now, if you notice, the compression from the source A is going to line up with the compression from source B right here, and also the rarefaction from source A and the rarefaction from source B line up here. And you can see right here in this line right here, we're going to have compressions and rarefactions that are all lining up with each other, and that's going to be constructive interference as they add to each other as the sound moves on. But if you notice in between, we got the rarefaction of source B and then the compression of source A that match up, and that's going to be destructive interference. And you can see that right here also. We got the compression from source A and the rarefaction from source B that line up, causing destructive interference. So in between, we're going to have destructive interference where the amplitude is going to be actually minimized and maybe even go all the way to zero. So as you move around, if you have these two sources that you're listening to and you move around here, you're going to hear a high amplitude. You move over here, you're going to hear a low amplitude, then high and then low, and the sound is going to increase, decrease, increase, and decrease and increase as you move vertically in this direction, because that's the properties of constructive and destructive interference. The Doppler effect is created because when objects make a sound, that sound is going to move away from wherever it was created at the same speed in all directions. But if the object that makes the sound, the source, is moving, then it's going to actually be getting compressions that are closer together on one side and further away on the other side. I would recommend looking at this website right here. It has a pretty good illustration and an applet for the Doppler effect, and it shows pretty well what happens with the Doppler effect. And you get compressions that are closer together on one side and further apart on the other side. If you've ever seen NASCAR or maybe even an ambulance that passes by, you get a high frequency as the object is coming toward you. So the ambulance has a high frequency as it's coming toward you, but when it passes by, it's going to have a low frequency as it's moving away. A train does this as well. As you have a train coming toward you, the whistle from the train has a high pitch, and then as it passes by, it's going to decrease and get a lower pitch as it's moving away. Now, breaking the sound barrier, basically what happens is if you get all these compressions, let's say you got a plane that's going as fast as the speed of sound. That means it's creating a sound, but the sound is staying with the airplane as it's moving. So you get a compression on top of a compression on top of a compression. Now, if you have air that has a lot of compression in one area, and it has moisture inside that air, then that moisture is actually going to condense and make a cloud. Each one of these pictures shows that you have this cloud right here that's being created, and if you notice, it's right on the engines, and that's because the sound that's being created is a compression on top of a compression on top of a compression that's compressing that air so much that the sound basically shows up in the form of a cloud. And you can see right here that again at the engines, that as the compressions all add up and they all compress on top of each other, you get the cloud that forms because of that compression, that moisture inside the air. And again, here you can see that compression adds up and forms a cloud right where the engines are. And the last example I have here, you can see the engines are actually in the back right here for this F-22. And basically, again, it forms those compressions on top of each other that form the cloud that's being created from all those compressions. So uses of Doppler effect, there's a lot of uses for it. We got echolocation that bats and dolphins use. Basically what they do is they send out a sound pulse, and when that sound pulse comes back at a higher or lower frequency, it lets them know if they're moving toward or away from an object. Likewise, weather can do this as well. Basically, a Doppler radar, what it does is it bounces a laser or a electromagnetic wave off of a cloud and comes back. And when it comes back at a different frequency, it tells the people who are doing the weather whether the cloud's moving toward or away from them at the time. Also, submarines do the same thing. Essentially, they're doing the same thing with echolocation, determining how whether an object is moving toward or away from them, as well as a police radar. That's how they determine how fast you're moving, is through the Doppler effect. Also, we know that the universe is expanding because hydrogen spectrum, basically hydrogen atoms will emit a very specific wavelength of light. And if that wavelength of light is shifted one way or another, then we can know that that whatever is holding that hydrogen is actually moving toward or away. So if the spectrum of the hydrogen is shifted towards the red end, then that means the wavelength is getting longer, which means the object is moving away from us. If that light spectrum is shifted towards the blue end, then we know the object is moving toward us. And almost everything we look at in the universe has hydrogen spectrum that are shifting towards the red end of the spectrum, which means that everything we look at in outer space is moving away from us, which is consistent with an expanding universe as it moves away. Resonance chambers, these are basically standing waves that produce inside of a chamber of a tube of a specific length. Types of devices that use these are kind of like your pipe organ or maybe your flute or something like that. And basically the resonance chamber, the flute or the pipe, it has a certain length to it. And with a flute, when you change the length, you're pushing the keys down in order to change the length of the tube. That's going to give you a different resonance inside of that tube. So the number of nodes and antinodes determine the wavelength of the frequency of the sound being produced. If you remember when we talked about standing waves have a certain amount of a certain wavelength depending on the number of nodes and antinodes. So we have this example right here that has two open ends. An example of this would be a trumpet, where you have one side you're producing the sound, and the other side you got the sound coming out, and it produces a standing wave inside. Now it's very specific on what frequency or what wavelength will be produced in here, because it has a specific length, and you can only have an antinode at both ends. So whether you start with antinode to node to antinode, then that's going to be half of a wavelength. Remember, this is only half a wavelength because you can only have a crest and a trough, or a compression and a rarefaction at one time. So this is going to be half of a wavelength. This right here is going to be the crest, trough, the crest. That's going to be a full wavelength for that length. And then this is going to be 1.5 wavelengths for that length. Now if we have closed end, one closed end, one open end, then that means we have a compression, a node at this end, and then an antinode at this end. Now we can have a node to antinode, but then if we have a node to antinode, we have another node and antinode in order to create our standing wave inside of a resonance chamber. And then we can have even more inside here, but we have to start with a closed end has to be a node, and the open end always has to be an antinode. So if we create a resonance, a very specific wavelength that's going to be resonating inside that tube, then it has to have an antinode at an open end and a node at a closed end. So an example that's done in class, basically we have a tube of water, and then that tube of water is allowed to raise its level up and down. And since it has an antinode at the top and the node at the bottom, if we use a tuning fork has a very specific frequency, which means that this distance right here is going to be very specific on where it's going to create a standing wave. So we have an antinode at the open end and a node at the closed end. For this, we have basically 1/4 of a wavelength. So the distance here is going to be 1/4 of a total wavelength. Also, if we drop that water level even further, then you can create another resonance. Basically, you have your antinode and node, but if you go down further, you got another antinode and another node, and that wavelength will be created and it'll actually resonate again. So every half of a wavelength distance down, it'll create another antinode and node, and it'll resonate again. And therefore, you're going to have the same frequency. It's going to resonate over and over again at different lengths, because they can create the same distance for their half wavelength as you continue to move that water level down. So in class, we use an E note, and inside the resonance chamber, it's loudest at about 0.26 meters, about 26 centimeters. And since that's 1/4 of a wavelength, because we have a node and an antinode, which is 1/4, we multiply that by 4, we get 1.04 as the wavelength. Now an E note has a very specific frequency. It's going to be 320 hertz. So we take that 320 hertz, then we multiply by the wavelength, and that's going to give us the speed of sound, which is 333 meters per second. So we don't have to use our conventional ways of finding speed, where we take a total distance divided by total time. So we don't need to shout and wait for the other person to hear us and then measure the amount of time it took the sound to get there. We can actually use a standing wave, where we can use the frequency of the tuning fork and then the wavelength of the resonance chamber in order to determine what the speed of the wave is going to be. All right, the next one, we're going to have a G note. A G note actually will create the loudest sound at about 21 centimeters inside the resonance chamber, which is 1/4. So we multiply that by 4, which is going to be 0.84 meters for the wavelength. And the tuning fork for a G note is going to be 384 hertz. So we can take our wavelength and multiply by frequency, 384 times 0.84, and that gives us a total of 323 meters per second for the speed of sound inside the room. And these are different frequencies for different notes. We actually are in class, we use a tube, a large tube, that we can use any one of these notes in order to determine the resonance inside that tube.